Hello and welcome to another video for quality assurance. We're going to talk about control charts in this video. Why we use control charts? Control charts are important to study a process over time. We need to look into the process over the time, and then we'll see if the process is stable, not stable, needs to be improved, or we should stick with the current process. So again, it's a tool that we use it to study a process to make sure that the process is in control. What does that mean? What does the process in control means? The process will achieve the goal that we plan for it. So we need to look into process variation. And if there's through the control charts, we will look into the variation, and we record it on the control charts. And basically, these are a powerful aids to understand the performance of a process over time. Before we start talking about the control charts, let's talk about the variation. There are several types of variation that we did talk about it earlier, but as a reminder, there are common cause variation and assignable cause variation. The common cause variation, these are coming from the random nature of the process. You can't avoid it. If you want to avoid it, you have to redesign the whole process. And that's just a slight difference in the process, such as the diameter, weight, service time, or temperature. Variation of this type is only removable by making a change in the existing process. So it's not, you can remove it, but you have to change the whole process. Assignable cause variation is, these are not part of the process. These happen because of a reason. The type of this variation arises because of special circumstances. Causes can be identified and eliminated, such as poor employee training, worn tools, machine needing repair. So these just an example. So again, the quality control tools will help us to study the variation of the process. And there are two types of variation, with a random variation or assignable cause variation. Variation means there are no two items or services are exactly the same, exist in the all processes. And you could find a variation within a one piece variation. This is just a variation within the single item or a surface. For example, a single square yard of fabric may be examined to see if the color varies from one location to another. So that's what we call the one piece variation. Not the second type of variation could be piece to piece variation, and the variation occurs among pieces produced at approximately the same time. For example, in a production run, filling a gallon jugs with milk, when each of the milk jugs is checked after the filling station, the fill level from jug to jug will be slightly different. So that would be from piece to piece, and that could be with a normal variation or assignable variation. Time to time variation. This is the variation in the production produced, in the product produced at a different time of the day. So for example, the comparison of a part that has been stamped at the beginning of the production run with part stamped at the end of production run. So there are three types of variation that we could see within the piece itself, such as the piece of fabric, and looking to inspect if there is any variation in the color. Piece to piece, such as the jug of milk, and you will see the level of filling is different from one, vary from one to another. There is a slight difference, and that would be a normal variation. Or time to time variation, for example, the production at the beginning of the shift versus the production by the end of the shift, or morning shift and an evening shift. These are the type of variation. Now, before we go ahead and talk about the the control charts itself. Why we study the control chart? We study the control charts because we need to make a decision. It is a decision making tool. They provide an economic basis for making a decision to whether to investigate for potential problems, to adjust the process or leave the process alone. So it is a decision making tool that will help us to investigate, go deeper, and see what's the cause of the problem. This tool will help you to make a decision on adjusting the process. Do we need to adjust it? Or maybe no, this is after studying the control charts, there's no need to change anything with the process, just leave the process as is. Control charts will provide information for timely decisions concerning recent produced items. If an out of control condition is shown by the control charts, then a decision can be made. Okay, now this is what we're looking for. If there is a out of control, this where we have to be careful, and this is where we make a decision about sorting, reworking the most recent production. uh, B, determine the process capability. It's important to see if the process capable for delivering the customer needs or not. And so the control chart will help us to determine the level of quality the process is capable of producing. Continual improvement in the production process can take a place only if there is an understanding of what the process is currently capable of producing. So far, we've learned that this is a decision-making tool. We study the control chart to see if the process in control or out of control. And if it's out of control, this is where we need to make a decision to maybe readjust uh, or buy a new machine or offer more training. And also, it's important to do the process capability to see what level of capability is the process is providing. Number two, control charts are problem solving tools. They point out where improvement is needed. They point out where improvement is needed. It's going the using the control chart will highlight exactly where in the process need to be improved. They help to improve a statistical basis on which to formulate improvement action, help locate and investigate the causes of unacceptable or marginal quality. By observing the pattern on the chart, the investigator can determine what adjustment needed to be made. So now, once we create the control chart, what we would do, we will study the control chart and look into the pattern. So if there is a pattern that has like a 5 points in a row that going up or down, that means the process are out of control, and therefore you have to uh, adjust the machine. So by looking into the pattern, you will be able to make the right decision. Utilizing statistical data leads to improved process quality. This is what we're looking for. The whole idea of using the control chart is to improve the process, to improve the quality, and we use it as a decision making tool. You can't just say, okay, well, I don't like the process because it's not a good quality. Well, you have to show that the process is out of control, and and therefore you could adjust the process. During daily production runs, the operator can monitor machine production and determine when to make the necessary adjustments to the process or when to leave the process alone to ensure the quality. So it is going to give you an idea on when to do the improvement, how to do the improvement, and the location for doing the improvement. So when and where to do the improvement. All right. Now, moving into some of the descriptive statistics that we will be using in the control chart. The mean, it's measure the central tendency, and to calculate the mean, we add all the values together divided by the number of values. The range would be the difference between the smallest, but the difference between the smallest and the largest. That would be the range, or what we use in Excel, minimum minus the maximum. Standard deviation measure the amount of data dispersion around mean, how far away from the mean, how clustered the data around from the mean. And the data shape, such as the normal or bell curve or skewed. That's another important that we will be looking and we'll be using in the control charts. So for example, here's a normal distribution. That would be the smaller standard deviation. As you see, this is clustered around the mean. Here's the mean, the middle line. And data are clustered around the mean. It's a narrow bell that's very peak. You see the peakness of the curve is it's stronger than the peakness of this one, so that has a smaller standard deviation. For the other one here, it has a large standard deviation, and there is more variation in the process. Looking into the other type, the skewed here, you will see that symmetrically distributed, which means that it is normal, but however, this one is skewed, which means most of the data shifted to the right. All the data clustered around this point right here, 16.2. And so that would call it the skewed, but normal distribution, should be symmetric and should look like the normal curve. All right, now for the process control chart, there are different types of control. This is basically the starting point for the control charts. And we're done with the background, why we use it, why we need it, and some of the descriptive statistics that we will be using. But here is the control chart. We started now. So the control chart shows sample data plotted on a graph with CL, that means the center line, UCL upper control limit, and a LCLL lower control limit. So here's a control chart, this right here. What is the control chart? It's a chart that shows the data around 3 points, the center line, the upper control limit, and the lower control limit. And we plot the data over time. And if we see something like this, we call it out of control, the process out of control. And now we have to adjust the process. We have to remove the variation. We have to reduce the things that cause the variation, and then that will help you to have a stable process. Now, there are two types of control charts. One is variable and one is for attributes. The variables one, it's for continuous data such as the length, weight, diameter, and time. These is something that we could measure. These things that we use it to like measure a length or a weight or a diameter or a time. However, the attribute, this is something that observed. It's not measured, it's counted. These values are discrete values, and these counted, such as percentage of defective parts, number of flaws in a shift, etc. So if you are dealing with something that you can measure it, that would be variable continuous data. If you deal with something that characteristic, that's something that you describe the data, such as yes or no, or how many bulbs are broken, that would be an attribute. And there is a big difference. So now we have to identify the difference between the variable and attributes, because once we know the data, we could pick one of these charts to use. All right, so one more time, what is the control charts? The control charts, basically, it's we've talked about the normal distribution, and we said this is the normal distribution, and this is a 2 sigma, 3 sigma, and this is how the normal distribution divided. This is the middle line, is the mean. Now take that chart and flip it to the right side. So like this, 90 degree, and that will give you exactly the same thing. So the control charts, it's basically the normal curve, the normal distribution, but it's flipped 90 degrees. So the mean would be the center line, and then you will identify the upper control limit and lower control limit based on the data that you have, based on the sigma, how many sigma you're trying to do. So just an idea on to get you closer to the control charts. We've done the histogram, we've done the normal curve, and now we're going to, instead of seeing it as a curve this way, now we're going to flip it 90 degrees, and we're going to plot the data. Now the data we will plot the data. In the past, we used to plot data here, uh, uh, here, and here. Now, what we need to do, the same thing. We're going to plot the data based on uh, based on the control chart, and the data will be around here. Exactly the same thing, but it's flipped 90 degrees, and that will help us to see if the process in control or out of control. If the process exceeded the control limits, that would be an out of control process. All right, now the X, we're going to start with the control charts for variables. These are, we have two charts that we use. These are X and R chart. X for the mean and R for the range. And these use monitor two variables. X and R bar charts reveals different problems. Is statistical control one on one chart out of control on the other, and in out of it's controlled in one chart and out of control in another chart? Is that okay? So what I'm saying here in this slide, there are two different measures. One is measure the variation based on the standard deviation, based on the average, but the other one is based on the range, and everyone uh, will give you a different interpretation. So for example, here we use the X chart, and we found that there is a 1 point that is out of control. However, this one here, if we use the R chart, we see that the process is in control because there is no data outside the borders, the limits. What does that mean? That means shift in mean detected by the X chart, but not by the R chart. So that means there is a shift in the mean. The mean has been shifted. It's detected by the X chart, but not by the R chart. Looking into here, you will see the X chart is in control. However, the R chart is not in control. You see this point is out of the control limits. What does that mean? That shift in dispersion detected by the R chart, but not by the X chart. So now we will see that there's a shift in the dispersion. Uh, it, it did not detected for the X chart, but however, it does detected by the R chart. So it is sometimes important to use both of them to ensure that the process is in control. All right, let's take a look into the difference between when to use the X bar and when to use the R bar. The X bar charts to monitor the change in the mean for the process. Central tendency, here we're talking about the central tendency. Now, if we're going to monitor the dispersion, we're going to use the R chart. If we need to monitor, again, the mean, that would be the X bar. However, if we need to use the R chart bars, the R charts, we will be using it to monitor the dispersion or the variability of the process. System can show acceptable central tendency but unacceptable variability, or system can show acceptance variability but unacceptable central tendency. So we need to make sure that we're doing both of these charts, the X and the R charts, to make sure that the process is in control. All right, to create the control chart, what we need to do, we need to, first of all, samples to be created or data collected, arranged into subgroups and taken during the process. So what you do, you go observe the process the first time, and you take 4 measurements, for example, measurement 1, 2, and 3, or 4, or you take from each production line 4 pieces to measure the length for a process. So what is important here, uh, I want to say that you cannot just only take a few samples and make a judgment on the whole process that is out of control. You have to get at least uh, uh, you have to do 3 measurements for each sample. So sample number 1, you take 3 or 4 parts, you measure it. Then you go to sample number 2, you take for parts as well. So I want you to take subgroups. The subgroups means the number of observation, how many times you observed that one sample. We'll take an example and explain it to you. The average of the subgroups values are plotted on the control charts. The central line of this chart shows where the process average is centered in the central tendency of the data. The upper control limits and the lower control limits calculated based on the describe the spread of the data. We'll see how the data are spread. Okay, collect the data, determine the trial central line, determine the control limits for the X chart, determine the limits for the R charts, then plot the data and examine the process and see whether if the process is in control after you interpret the chart, whether the process is in control or out of control. All right, let's take a look into this one here. We have 5 observations for these 5 samples. What we do, we look into the 5 observations. And this is sample number 1. This is happened at 7:30 on this date. And we found out the measurement to be 11.95, 12, 1203, 1198, 1201. Add them together. You find what would be the average of the X, the average of these, the average of these. That's the average. That's the X bar. And the range, you subtract the maximum minus the minimum, you find what would be the range. So number 1 is you take the observation, you take the sample 1 and you take 5 samples of these, 5 observations of these, and the same thing you do for sample 2. Sample 2 is taken at 7:40, and you take the average of these and you list it here, and you do the same thing for the range. And sample 3, after 10 minutes, you take another 5 parts or another 5 observations. It depends on what the process is. This looks like assembly. And you do the average, the same thing for sample 4 and sample 5 as well. Each of these samples, you take 5 observation. And now what you do, you take average of the average. Now, how you do the average of the average? After you find the average for each one of these, you add them together, you divide them by number 5. So we have 11.99 plus 12 plus 11.99 plus 11.99 plus 12.02 divided by 5, and that will give you the X double bar, the X double bar. And for the range, you take add all these ranges and divide them by 5. That will give you the R bar. Now, to do the control limits, the upper control limits and lower control limits, there are different ways for doing it. One is using the standard deviation, the sigma, and one is using the appendix. One, if you know what the standard deviation for the process, or you can calculate the standard deviation for the process, you could use this these sets of equation, this one right here. If you don't know what's the standard deviation for the process, it's hard to do it. What you do the A2 based on the number of observation. And in this case, you need the R bar. Okay, upper control limit would be the X double bar plus or minus, it depends on upper control or lower control, the 3 sigma. Upper control limit also or lower control limit can be calculated by X double bar plus and minus A2. And this is taken from Appendix 2, I believe. Appendix 2 taken, and you can find it on any website. There are a lot of websites that will provide you what would be the A2 based on the number of observation and times the R average. Okay, for the R, the control limits for the R, that would be the upper control limit for the R would be D4 times R average or D3 times R average based on whether you're doing the upper control or lower control. The upper control will be D4 times R, lower control would be D3 times R. And this is taken from also from the Appendix 2 for the control chart. So you will find it on Appendix 2. There's another chart that we could use as well called the standard deviation chart, and very similar to that, but I want to keep it simple. I want you to focus on just very few charts, the X and R and P and C charts. But for more information, I'm going to talk about the standard deviation chart, which would be calculated using these equation. The average of the standard deviation, you take the standard deviation for each one of these samples and divide them by 5, for example. And then for the upper control limit and lower control limit, you do B3 or B4 times the S bar. All right, now it's time to take a look into the exercise. The following collection of data represent samples of the amount of force applied in glowing process. So we have a glowing process, and we need to look into the force applied into the glowing process, determine if the process is in control or not by using the upper control, lower control, X and R charts. All right, so here's the samples. We have 15 samples. Each sample we took 5 observation, 1, 2, 3, 4, 5. And now what we need to do, we need to create the control chart. So what I want to do here, I'm going to stop sharing this screen. I'm going to go to the Excel. So I could show you how to do this using Excel. All right, so what I did here, I opened an Excel sheet, and these are Excel templates that I provided on my D2L shell for the quality assurance. So if you go to the D2L, you will find some templates that you could use. And so what I did, I copied the data from the charts that I have on the slides, and then I applied it and copied it in here, adjusted the template to fit it was this way. So I did adjust it to fit 15 samples. So we have a 15 sample, 5 observation. So the first thing that you want to do is find the average. So let's go ahead and work on this. And these charts will generate by itself if you use templates. And there are so many templates, whether from ASQ or from online. Just Google SPC template, statistical process control templates. For X charts and R charts, you will find so many templates if you can't get access to these templates that I have. All right, so if you are one of my students, you should be able to access through the D2L, but if you're not one of my students, then what you need to do is Google it or contact me by email and I will send it to you. So anyway, so we have 15 samples, and if for each sample we took 5 observations. So first thing you want to do is find the average. So we do the average for each one of these samples, close the parentheses, and now you double click on the lower right corner, and that would generate the averages for each one of these. Double click to check that you took the correct data, and it is. And now for the range, that would be the maximum of these data minus the minimum of these data again. And double click on the lower corner, and that will give you the ranges. And now the next step is to find the X bar, the X double bar, and the R bar. The X double bar would be average of the averages. So we did, after we calculate the average for each of these samples, we calculate the average for these. So, and that would be equal average. You type average and select this column only, the average of the data, and click OK. Same thing for the R bar. What you need to do is average and select all these data here. Close the parentheses and click OK. Excuse me. And now we're going to work on this. And this is exactly what's going to create the charts for you. So I'm going to delete all this. So there's no charts anymore. Excuse me. All right. Now we're moving into, so the first step, we did find the X double bar and the R average. And these are the center line. These are the center line. So what you want to do here, go to the, forget about this here. I'm going to delete this for now. Do not look into this at all. So this is just because I took it from a sample. So what I want to do is I want to cross these so you don't want to be confused about it. So these are, forget about them. Just focus here. The center line would be, what would be the center line for the X chart would be this one here, 10.73. Now let's talk about the lower control and upper control. Starting with the lower control, there are two equations. One equation is using the A appendix and one is using the standard deviation. So what I want to do here, I don't have the standard deviation. So one way is to calculate the standard deviation for the samples for each one of these. And that could be easy as standard deviation for the sample, and select all of these and close the parentheses, and that would give you what would be the standard deviation, 0.1. Uh, another way for doing it, is to okay, so we have the standard deviation. This is the standard deviation. That would be the sigma for the process, the standard deviation. All right. So let's use the standard deviation first, and then we will use the A2. So for the standard deviation, let's do this here. So for the lower control limit would be X double bar, which is the average that we have it here, 10.73 minus 3. Now for this one, for the standard deviation, we just calculated to be this one here. Click OK. And now we're going to do the same thing. We're going to copy the same formula and paste it here. The only difference would be is the plus. So now would be adding the 3 sigma. So the upper control limit would be 11.04, 10.42 for the lower control limits. Okay, now we could do the other way, which is using the other equation, which is A2. And if you go to the appendix 2, and we find the observation of 5, you will find that A2 to be A2 for 5 would be 0.58, 0.58, 0.58. All right, one more time. What I did, I went to the table, and this is basically the table. I have it here on a side, so I'm going to copy it as well here so you could see it, what I have here. All right, here we go. I'm going to put it here. So if you look into the number of samples, we have 5 observation for each sample. A2 would be 5, 8, 5, 8. So I came here. I said, okay, I want to apply this equation for the lower control limit, X double bar, which would be this one here, minus A2, which is 0.58, 0.58 times R average, which is this one here, 0.22. And close the parentheses. Make sure to put the parentheses here to give priority for the multiplication, and that's would be 10.6. And now let's do the same exact thing for this, but what we have to do, we change the minus to plus. All right, so that would be 10.85. Okay, now somebody will say, well, you got different values. Yeah, sure, for sure. I use different tools, different techniques, so you should get the different values. However, the final result should be the same if it's within control or out of control. Okay, so now we did calculate the center line, the lower control limit, the upper control limit for the X chart. Now let's take a look into the R chart. We have the average of the range would be 0.22. Now let's take a look into the equation for the R chart would be the D4 times the R or D3. So let's take a look into the lower control limit first. D3 for n equal to 5. This example have n equal 5. We have 5 observation for each sample. So let's take a look. D3 for 5 is 0. And D4 for 5, D4 D4 for 5, that would be 211. 211. All right. So now we're done. Now let's do the calculation for this lower control limit and upper control limit for each one of these. So the center line would be 0.22, which is taken from here. That would be the center line, the average of the ranges. Lower control limit would be 0 times the R, which is this one here, D3 times the average of the R, which is 0. And for the upper control limit would be the 211 times 0.22, which is the D4 times the average. That would give you 0.47. And now let's go ahead and plot the chart. So we're done with the equations. So we'll put them on the side here for a second. And let's take a look into how we're going to create this both charts. All right, that's maybe too. All right. Okay, so now here we're going to create the charts. And this is for the X chart, and this is for the R chart. For the center line, for the first sample would be 10.73, and this is taken from here. And that would be for all the samples from 1 to 15. That's the center line. And now if you look here into the chart, you will see that the center line has been created. And now let's take a look into the lower control limit. The lower control limit is equal to this value here. And I want to lock the value. It's here, 10.47 actually. And I want to lock it so I could copy the same value for the rest of the cells. Double click. Same thing for the upper control limit. That would be equal to 11.04. And a double click. And for the sample mean of these, we have to look into each sample and find out the mean, which is we did the calculation here. So for sample 1, the mean for that would be 10.73. Let's take a look into the chart now. We have the center line, we have the upper control limit and the lower control limit. And click OK now, enter, and you will see the first dot has been created on the chart. All right, here we go. Here's the first dot. And now for the rest of the dots, we're going to double click to copy the cells from here to here. And as you see, the chart is very stable. The process is stable and in control. As you see, it's all the data around the center line. And we do the same thing for the R chart now. All right, lower control limit would be this value, which is 0. I'm going to do 0 here. Double click, lower right corner. And for the center line, you see this is the dashed line is the lower control limit. The center line is 0.22. And now double click as it's created. Upper control limit would be equal to 0.47. Lock the cell $sign before and after. See the center line has been created, or the upper control limit has been created. And now double click and we'll see the upper control is right here. That's the center line, that's the lower control, and this is the upper control. It's nice to use these kind of templates that will help you to save some time in creating the charts. And now for the sample range, we take these here and we do the same thing here. And as you see, this range chart is out of control, and that's for data 8, for the cell 8 right here. And what we have to do, we have to investigate what was happening at that time and how we could solve the issue if there is any issue for sample number 8. It seems there's an extreme value on that value. So that how we this is how we calculate the X and R chart. As we see, this is in control, this is out of control. Is the whole process is out of control? Yes, it is out of control, as we did talk about using two different charts to determine if the process is in control or out of control. And we found out that the example that is given, it's saying if the R control is out of control and the X chart is in control, that means shift in dispersion detected by the R chart. So we need to look into, there's an extreme value, it seems here on 8 that exceeded all the values from the previous one. All right, with that said, I'm gonna end my video here, and I'm going to create another video for the R, for the attribute charts, which is basically the P and C chart in a different video. There's another software that I want to talk to you about it for advanced skills, which is using Minitab. Minitab is a fun software that you could use to do all the calculation in a click. It's actually, you don't have to do these equations or anything. Is all you need to do is put the data and go to the control charts, and the Minitab will create it for you. Well, I will make another video for that in particular. With that said, thank you so much, and I'll see you in another video.